so throughout this whole subject, we run into a basic fact of statistical mechanics, namely that the probability of things happening have to do with the energetics. If this state is more energy, is at a higher energy than this state, then the higher energy state will be less occupied, et cetera, et cetera. So this is a basic fact of, basic principle of statistical mechanics. And I wanted to go through the statistical mechanical argument for the occupation probability of a receptor, where there's a receptor and it's in some kind of medium where things that it can be bound to are moving around. And I wanted to get the statistical mechanical expression for the probability of the receptor being occupied. I mean, we've already gotten such an expression in terms of the rate at which, if it's occupied, the thing that is bound to it comes off, right? The unbinding rate. But I'd like to compare that, I'd like to connect that with the binding energy, all right? Okay, so the basic principle of statistical mechanics is that you have a system and there are a collection of states that it can be in, right? So if it's a particle moving around in a box, it can be at different places and it can have different momentum, all right? That completely describes a particle, where it is and what its momentum is. Velocity, but it's better to think of momentum. Okay, so there's a thing called the partition function, which is the core object of statistical mechanics. And it's very simple in concept. It's just the chalk is terrible. It's the sum over all of the possible states. You imagine labeling them by something. I mean, eventually, in quantum mechanics, it's really a sum over integers, because the nice thing about quantum mechanics is that states are discrete, except, well, it's easy to make them discrete. And each of these states has an energy, and we are in contact with a heat bath at some temperature T, and the partition function is this thing. And the great thing about this is that, you know, if there's some particular state, or suppose there's some particular state you're interested in, and you want to know, okay, so what's the probability that it'll be in that state? Well, it's easy. The probability is just e to the minus beta energy of that state divided by z. And there are various ways of setting things up such that really all you need to know is z, and then there are various manipulations that you can do on it to get anything that might be of interest to you. All right, so let's do the following thing. Oh, okay, and of course, when you say something's a probability, it better be positive, it better be less than 1, it better sum, if you sum over all possibilities, to 1, and that's all guaranteed here. All right, so we want to look at a particular case. We have a box. We have a particle that can move around in this box. And of course, it's connected to a heat bath. But we're going to add one little thing. There's a something. Let's think of it as a receptor. There's a little object to which this guy that's otherwise moving around could be bound. Okay? And when he is so bound, then there's an energy involved in that. Okay? All right, so what's the partition function for this guy? Well, it's sort of simple because what are the possibilities? This guy can be bound to the receptor and not moving around. Okay, so that's a contribution, e to the minus beta. Let's just say the binding energy is epsilon. Okay, and then it could be, so this is bound. And then there's all the ways in which it can be not bound, all right? So how can it be not bound? Well, it can be at different positions. So this box has some size, and this particle can be moving around. It can be in different places. And in the different places, he can have a different momentum. And if it's three-dimensional, you have to do an integral. And it is, okay, Beta, by the way, is just 1 over kT. It's just a convenient notation. His energy, when he's moving around, doesn't depend on where he is, but it depends on his momentum. Okay? Now, there's something a little bit funky about this, because this has units, momentum times position cubed, and this guy doesn't have units. So this is where quantum mechanics comes in. In quantum mechanics, you, in effect, learn what is the right way of making this free of units. And the answer, the quantum mechanical answer is that this integral over position and momentum, that's called phase space, has natural units. Well, let's just say h, Planck's constant. So h has the units of momentum times length, and if I divide this integral by h cubed, it becomes dimensionless just like this guy is. So this is what quantum mechanics has taught us about. The people in the 19th century who understood this whole story had a little bit of a problem. They figured out, they had to say, well, there's some kind of minimal size to the volume and phase space that you can integrate over. We'll just put in some delta. We don't know what it is. And for lots of things, it doesn't matter what the delta is. But for some, it does. And that was one of the first things that the quantum revolution cleared up for us. OK, so this is an integral to be done. And the integration over the position where you are in the box is going to give the volume of the box. And the integration over momentum is going to give you something that's going to depend on momentum and mass and all the rest of that stuff, and temperature. So there's an integral to do. And when I'm all done, and I divide by Planck's constant cubed, I'm going to get something that has dimensions of length cubed. And this is the so-called thermal de Broglie wavelength. You know that if a particle has a momentum, it has a wavelength as a quantum particle, and that wavelength is h over p, where the p is the particle's momentum. Well, in this case, I'm integrating over the momentum, but there is some mean momentum associated with the fact that it has a temperature, right? So, p squared over 2m, the kinetic energy, is something like kT. And as a matter of fact, it's more accurately 3/2 kT. So the mean value of momentum that goes into this formula is going to be determined by the mean kinetic energy is 3 degrees of freedom times 1/2 kT for each one. And so you can put all of this into this formula, and you'll get something which is the de Broglie wavelength of a particle whose momentum is the momentum associated with this temperature, which means there's a mean momentum that's determined by the mass and the temperature according to this kind of relationship. Okay? So this is a funny thing. It depends on the temperature, it depends on the mass, it depends on h. I just call it thermal, lambda thermal, right? It's the hotter the particle, the hotter the temperature, the smaller this wavelength. Okay, so that's what happens if you have one particle. Oh, and so let's finish this up. So remembering all of this, we can say, okay, so this z is equal to, put it here for a moment. Okay, so it's e to the minus beta epsilon plus the volume over. So this is a nice normalization thing. Okay, so what's the probability of occupation of the receptor? Well, here's the term that comes from the receptor being occupied. So that's e to the minus beta epsilon. And I have to divide that by z. So I divide it by e to the minus beta epsilon plus v over lambda thermal cubed. All right, so we're getting close to the goal. Not quite there yet, but getting close. So we have an expression for the occupation probability of this funny little trap here. in terms of the binding energy of the particle when it's in the trap. Okay, so the idea is, here's energy, here's 0, here's the energy of binding, and when he's in the trap, his energy is this, epsilon. When he's not in the trap, his energy can be kind of anything with some mean that's determined by the temperature. All right? Okay. So that's one particle. All right, but we've been talking about situations in which there's some density of particles. So we have to generalize this a little bit and ask, so how do you go through this argument when I have not one particle, but n of them? Okay, so n of these guys wandering around. And some of them, any one of them can be bound. And when we were doing our study of the occupation of some receptor on the surface of the cell, we knew that there are many, many different molecules of interest outside the cell, and which one decided to be bound at any given moment didn't concern us. We just wanted to know, is it bound with one of these molecules or not? All right, so how do we, so n particles. So how do we generalize this to the n particle case? All right, so that's what I want to do. Well, I just have to generalize this slightly. All right, so what we've learned, so we have for the single particle, we have an expression which is beginning to look interesting in the sense that it's dependent on the volume. Well, I have one particle in a volume, so 1 over that volume is the actual density of that particle. And it depends on the binding energy, epsilon. And it also depends on the temperature through other terms, but beta is the most important one. So let's redo this whole thing for the case where I have n particles. Okay, let's see what happens. So let me erase this because we're going to be really, all right. All right, so that's for 1. All right, so what about for n? Okay, well, if there are n particles, there's still really 2 conditions. Either this receptor has one of them bound to it, or it doesn't. That's the only, we're not letting more complicated options be exercised. So let's suppose nobody is bound to the receptor. So I could just forget about this. And what I'm doing in summing over all of the states is this integral. This is the integral for one of the particles, and there are n of them. So all that happens is I raise that to the nth power. All right, so that's this integral d3. Well, I know what the answer is for this term. I'm going to say it's v divided by this funny number. Okay? So that integral raised to the nth power. This is just to say there are n different particles wandering around completely independently. Each one of them gives me such a contribution, and it's their product which comes in here. Okay, so, and then there's one of them is bound. Well, which one? There are n of them that could be bound, so there are n different things I could put here. And then, well, the other ones are wandering around, but there are only n minus 1 of them. To the n minus 1. Okay? So this is the generalization of what I just did for one particle for n particles. And so there's some factors of n lying about that are going to turn out to be important. N divided by the volume is the density of these guys. Okay? So what's going to happen? So what I'm interested in, So the probability of this guy being occupied for the n part, I don't know, p n sub occ, okay? Well, basically that's this term divided by z. In other words, this term is the sum over all of the states where one particle, where the receptor is occupied once. So this is, so to say, this is the weight of states where the receptor is occupied once, and I have to divide that by z, which is the sum over the weights of all the states. All right, so the final answer is going to be n e to the minus beta epsilon times this v over lambda cubed to the n minus 1 divided by the same thing, v over lambda cubed to the n plus the same thing, n over e to the minus beta epsilon, v over lambda cubed to the n minus 1. All right, so it's not yet, remember we had a formula for the occupation probability which went something like concentration divided by concentration plus some constant, which we called C half. Remember, this is what we're going for. P occ is something like concentration divided by the concentration at which the probability of being occupied is 1/2, right? And so really our question is how to look more deeply into what is this C half. In the previous discussion, we got this in terms of the off rate of something that's bound and a bunch of other things. Okay, so now we're trying to get it in terms of an even more fundamental quantity, namely the binding energy. Okay, so we're almost there because, well, we can obviously do a certain amount of dividing out, all right? So let me divide out n minus 1 powers of v over lambda cubed, all right? Obviously, I can do that. Each of these terms has such a factor. So I can erase this guy from here. I can erase him from here. And I will leave one of these guys here. Okay? All right, so I'm almost there. N over V, N over V. Yes, okay, so, and I can go, all right, so I'm almost home. Each of these terms has either an N or a V, right? So I can divide out, suppose I divide the top and the bottom by N. Seems like a good idea. So I divide the top and the bottom by V. So I get rid of that V. I turn this into N over V, and I turn this into N over V. Suppose I multiply top and the bottom by e to the plus beta epsilon. So I'll get rid of this term, the e to the minus beta epsilon here. I'll get rid of it here, and I'll put in an e to the plus beta epsilon in that term. All right, so if I do that, get rid of this guy, get rid of this guy, but supply it down here, e to the beta epsilon, and bingo, we're home. All right, because N over V is the concentration. It's the number of molecules in the volume divided by the volume. That's the density, all right? So this is C divided by C plus e to the, for e to the beta epsilon divided by this funny thermal de Broglie wavelength. And that's exactly the kind of formula we got from our kinetic argument before, all right? So we've identified, so C half, I guess, we're now just discovering that it's determined, it's related to, it's governed by basically by the binding energy. And in the previous incarnation, what did we have? I never, there are factors to be remembered here. So what we had in the previous incarnation was C half equals, right, 1 over 4 d a distance and tau b, or something like that. All right, so this is what we got for the C half using our, so to say, kinetic argument. There's an unbinding rate, which is 1 over this unbinding time tau, and then there's an on rate that has to do with the diffusion constant of the molecule and the size of the target, okay? So that's what we got from the kinetic theory. What we get from good old straight up statistical mechanics is something that involves the binding energy. So this is telling us how the off rate depends upon the binding energy, all right? This is so the most sensitive thing is this exponential here. So this is saying the more negative the binding energy, the stronger the binding, the slower the off rate is, the longer this binding time is. Okay, so this is the argument I wanted. This is, really these guys have to be thought of as in solution. I'm just treating them as molecules in a gas, but the essential fact that ultimately the half concentration, the concentration associated with 50% occupation probability is primarily governed by the binding energy. Okay? All right, so we're going to use this fact a lot. Okay, so let's see. All right, so yesterday we finished up sort of discussing the physics of how the E. coli molecule, how the E. coli bacterium, not able to detect the gradient of the concentration in its immediate neighborhood, finds its food by essentially looking at how the measure of concentration in its neighborhood that it gets from its receptors varies with time as it moves, all right? And so the whole question was, can you set up some kind of set of reactions that implements this? That is to say, you have the receptor, it binds and unbinds at a certain rate, but then it causes something to happen inside the cell. You know what it has to do. It has to modulate the rate at which the flagellar motor is switching from going clockwise or counterclockwise. And so there was a fairly elaborate reaction system that people actually, piece by piece, reconstructed by doing cloning and mutation and whatnot. The whole collection of proteins that are involved in that whole circuit were identified painfully over about 20 years of work. And we have I would say, a clear qualitative vision of how it all works. And the one thing that the set of equations that I showed you and that you can read about in the one of these textbooks that I mentioned, the one thing that it doesn't quite cover is the fact that there's adaptation. That is to say, and I'll just restate what the problem is, and rather than, we have to augment the reaction system one little bit in order to understand a very important fact. Okay, so if you have if the cell is sitting in some concentration, so let's plot the concentration as a function of time, and the concentration is doing this, nothing, all right? Then, you know, I can plot below it the switching rate. The motor is always going with some preference for one direction or the other between clockwise and counterclockwise. So there's some switching rate. And I should have colored chalk to make this really work. Okay, so you can do an experiment in which all of a sudden you change the concentration, all right? And that'll cause the switching rate to change. And the question is, okay, does it change and then stay at the, you know, elevated level, or what? Now, in fact, there's adaptation. That is to say, whenever the concentration is constant, the switching rate is observed to relax back to some constant value that's always the same. This is a little bit like your, you know, the adaptation of the eye. So what really happens to the switching rate is that when you bump up the concentration, the switching rate changes all right, but once the concentration comes back to constant, the switching rate relaxes back to the value it had before. That's called adaptation. So the switching rate is the same no matter what the level of the constant level of concentration is. So this is a little tricky. So this is adaptation, and you have to go. Let's see if I can find the picture. All right, so now this gets tricky. Where the hell is this thing? Thanks. All right. No, it's okay. I know where. I should know where I am. Lecture plan. Here we go. All right. Yeah. All right. So, share screen. Go to this guy. Full screen. Yeah. Okay. Yeah. So, we had this complicated-looking thing, and in order to implement this adaptation, basically, what has to happen, and there is indeed a protein that does it, that as the motor adapts, there's a back reaction on the receptor. And the sensitivity of the receptor to the binding of the molecule that it's designed to receive is modified. And there's a simple scheme which makes it essentially automatic that adaptation takes place. Okay, I think I just put this in your head so that you know it can be done, but it's a question of finding all of the reactions that are going on and verifying that they're coupled together in such a way that the desired result actually occurs. And I think I'll leave it at that because I want to get on to another issue about coupled reactions in biologically relevant processes, and this would take me too far afield. But if you want to follow it up, what I can highly recommend is, okay, so, the one thing that I haven't put on this collection of slides yet is my recommended list of textbooks. Okay, so there's a textbook called Biophysics Searching for Principles by Bill Bialek, my very energetic colleague, and there's a really nice section in that book on this problem. Okay, so for the moment we'll leave it behind. If by miracle, if towards the end of the week we have 10 minutes or half an hour to talk about this, I can go back to it. It was a problem that bedeviled people. It was really only solved conceptually in around 2005 or 6 or something like that. There was a missing link. There was a protein that whose existence people knew, but what it was doing for you was not clear. And what it was doing for you was essentially providing a feedback loop so that when the motor switching rate changes, there's a feedback on the receptor that basically changes its level of response to binding of the target molecule, all right? And you have to analyze the details in order to get the full story. Okay, so that's where I want to leave Bergen-Purcell and noise in sensing. Okay, so what I'd like to do now is to, I should ask if there are questions. You're free to, yes, sure. He has a question. I don't know what it is, unfortunately. The dog.
Due to this mechanism of feedback,
yes.
What actually changes could be this energy of binding? That
could be, yes.
Could be.
That's fine, yes. That's, unfortunately, the problem in all of this is proteins are complicated, right? They're big things. They have lots and lots of degrees of freedom. And understanding what they do and how they do it a priori is difficult. So I'd say the approach that I'm talking about here is one where you say, okay, taking the bull by the horns and actually looking at the structure and modifiability of the structure of a particular protein is a hard job. Let me look at the structure of the reactions that are going on without specifying in detail how they actually do their thing, and say, okay, is there some link that I could add to the system of reactions that, if the parameters were right, would give me this general phenomenon like adaptation, right? So once you've convinced yourself that there is a link that you can add, a feedback link, for example, that could do it, then you can start looking at your list of 20,000 proteins, right? If you're looking at some higher animal, and see, is there in there one that could possibly carry out this kind of enzymatic reaction? And then do real experiments, verify, et cetera. So this is trying to find out, okay, never mind the details, what's the structure of the reaction system that has a chance of carrying out the function that we know has to happen. All right? So adaptation is a very general thing, and looking for the structure of the reactions that could do it is something that makes sense. And what I'm saying is that during, how shall I put it, it took a while to figure out what is indeed the kind of feedback loop, just the general kind of feedback loop that is needed in order to achieve adaptation. All right, so what I want to talk about today is the phenomenon of kinetic proofreading. And as you will see, first of all, I have to identify the problem, and then we will be led into a discussion of possible reaction networks that solve the problem. Okay, so the problem is essentially the generic problem would be something like this. For various reasons, I might want to make a polymer that has, it's just a sequence of units. And it might be that there are two kinds of units. In fact, maybe I should call them right and wrong, okay, or something like that, R and W. And I have a soup of these guys. And what I'd like to do is to create a polymer which is just connecting these guys together. All right, you can see where this is going, right? I would like to, and so I have some enzyme. And this enzyme has the property of, given a polymer, it'll pick out of the soup, hopefully, the right, let's say E sub R, I have one polymer that's supposed to take a growing, one enzyme that is supposed to take a growing chain of the right elements and simply add a new one. Okay, and then it goes back and picks out of the soup another one and adds it, and so on. All right? And let it be the case that, you know, there are two similar looking guys, and the enzyme has to distinguish between them. So it's possible that the discrimination that this enzyme can achieve is not perfect, and that sometimes it'll put a wrong in here. Okay? And the question is, now of course you understand where this kind of thing is relevant. It's relevant in copying the DNA in the genome. It's relevant in translating an RNA message into protein. It's, well, let's think of those two as the most common examples. Actually, there's yet another one that has to do with fabricating proteins. But in any case, so in the case of copying the DNA, well, the soup consists of the nucleotides, right? The A, C, G, and T nucleotides. And at any given step in the proceedings, the DNA polymerase has got to pick the right, it's copying a strand of DNA already, and it's gone some distance, and now there's a new nucleotide that has to be added to the growing double-stranded DNA that you're copying from the original single strand, and it has to pick the right nucleotide out of the soup. All right? So the generic problem is this, that is to say, you have an enzyme. It has multiple substrates that it can act on. Well, I guess let's see, what is the substrate is both the polymer that's growing. Well, there are various ways of, it can be simplified. Okay, so maybe even the most simple thing is we don't even have to worry about the growing polymer. So let's look at it this way. Okay, so let's see. So here's probably the most primitive version. The cell has a problem of when it's creating new proteins, it has to have transfer RNAs. That is to say, a transfer RNA is a special RNA that has a codon at one end. In fact, I have a picture here somewhere, so might as well have a look at it. Yeah, okay, so, no, never mind. Oh, you have to switch that, okay. Yeah, so what's a transfer RNA? Well, there's an example. At one end, it has something that's called the anticodon. That is to say, it's supposed to recognize on the message a triplet of bases and, so to say, connect that to the appropriate amino acid, right? So there are 20 amino acids hanging about, and each one of them is associated with a codon triplet. And there are therefore 20 transfer RNAs, or maybe only 19 because they're stop codons. So these transfer RNAs are made in the normal course of events, but at some point, somebody has got to pick, so a particular one of these transfer RNAs is floating around, and it's not useful unless at the other end of it, it has the correct amino acid attached. So there's an enzyme, an amino acyl transferase or something like that. There's an enzyme which basically is designed to take, let's say, this particular guy who needs to have a phenylalanine attached to him. And so this enzyme, on the one hand, you know, it takes this proto-transfer RNA and it attaches one amino acid to the other end. And it's supposed to attach the right one, all right? The one that's, so to say, coded for by that triplet. And it has ample opportunity to make mistakes because there are 20 amino acids floating about in the soup, and some of them are structurally very similar. And basically, so let's say transfer RNA charging. That's kind of the core event. So, so I have the enzyme, never mind its name, but it's associated with a particular amino acid. Let's suppose it's the one that's supposed to put an alanine on the appropriate transfer RNA. So there's a transfer RNA that comes along, and so this is an uncharged transfer RNA that's supposed to get an alanine added to it, but it's not yet added. And then in the soup, I've got alanines, I've got phenylalanines, I've got isoleucine, et cetera, et cetera, et cetera. I have a density of all of these guys, and the output is supposed to be the transfer RNA charged with the right thing, okay? And there's plenty of opportunity to charge it with the wrong thing, okay? So, and the reaction involved looks pretty simple. So let's look at the reaction in a schematic way and write down okay, so let's look at the reactions that can do this and try to figure out what can we say about the error rate. And the idea is going to be that, okay, this all works because there's some binding energy of the alanine to this particular transfer RNA, whose structure I showed you. And, well, the good guy has some binding energy, which is greater than that for any of the bad guys, but maybe the difference between the good guy and some not so good guy is not that enormous. But what does that do to the error rate? Can we be specific about that? Okay, so this is called chemical enzymatic sorting. So let's look at the reaction kinetics of enzymatic sorting to see what the problem is, and then hopefully before the end of the lecture, a solution to the problem. All right, so the kinetics of enzymatic sorting. Okay, so what's the deal here? So there's an enzyme, the transferase, amino acyl transferase. I have trouble remembering all of these these names, excuse me. And it's got an opportunity to pick either an A or a B. Let's suppose it's just binary. So what happens? Well, it grabs onto one of these guys, either A or B. And then what happens next? Well, if everything goes right, this then makes the product. Enzyme plus product. So what is the product? Well, the product is the charged transfer RNA, and it's the good product. How to recognize this? All right, so this is a typical enzymatic reaction. You have an enzyme, you have substrates, a substrate binds to the enzyme then does something to the substrate. In this case, it makes the transfer RNA with the appropriate amino acid stuck to it. Okay, and actually there are rates here. Okay, so let's have a look at that. The on rate is going to be some kind of reaction rate times the concentration of the thing you're trying to pick out a solution. Okay, so the more of this you have, the faster this process is going to go. There's also an off rate. Goes the other way. We'll call that K minus. And then if it decides to go, this will happen at some rate, which we'll call V eventually. All right? Now, the problem is that there's a competition between A and B. This guy could charge the enzyme with B, and B could go to, it'll release the enzyme plus the bad product. So product transfer RNA with the wrong thing attached to it. And this will have some rate. So I've got K plus B concentration. Now, maybe the charging rate for B is a little bit different from that for A. Could be, we don't know. And there's this guy, K minus. I'll put a prime, okay? So to separate these things, and there's possibly a V prime here. So, in cartoon fashion, that's what's going on here. It's a typical enzymatic reaction, okay? And our concern is presumably, you might say that the concentrations of A and B are not that different. Let's take that as the situation we want to deal with. And we certainly want, on the other side, the concentration of the good product to be a lot bigger than that of the bad product. How well can we do? All right, so there's this a scheme for solving this problem was proposed back in 1974 by John Hopfield and Jacques Nino independently. And well, first of all, we'll go through this a little bit. And in the context that they studied, this simple scheme leads to an undesirable result, as we shall see. Okay? So let's see what happens. All right, so we can translate this scheme into equations. Okay, so equation number 1, maybe I should put the equations over here. All right, let me put the equations over here. All right, so we're going to do the dynamics of enzymatic sorting. These are the kinetic equations. All right, so, well, how about the rate at which the enzyme bound to A, how rapidly does that increase? How many of these guys are there? All right, so there are two things happening. Stuff is going on. So there's K plus concentration of A times the concentration of the enzyme. That's on rate. And then there's off rate minus the off rate. So there's two ways this bound complex can undo, right? It can make the product or it can go back. Okay? So there's two terms here. There's K minus plus V, the reaction rate, and that's it. And there's a similar one for B, d dt bound to the wrong guy. So this is going to be K plus prime, B, same old enzyme. I'm sorry, and I'm missing something here, of course. EA. All right, so the heart of the matter is going to be that the off rates will be different. When the enzyme is bound the good guy, the off rate is small. When the enzyme is bound the bad guy, presumably it can tell the difference and it kicks it back out more frequently. All right, so there's a K minus prime, and then once it's bound, B. And the other thing we have to know is the total amount of enzyme present plus, well, is certainly constant, right? The enzyme doesn't get, that's the whole point about enzymes. Their total number stays fixed. Okay, so that's the combination of how many enzymes are bound to A, how many enzymes are bound to B, and how many enzymes are free. Right, so the enzyme can be in 3 different states. It can be just hanging about all by itself. It can have bound the bad substrate, or it could have bound the good substrate. So, okay, here are the equations. They're trivial. And what do we want to do? Well, we want to know basically, what do we want to know? Well, we want to solve these guys. Okay, so we'd like to solve this in steady state. So all the DDT terms are 0. So we just want to put all of this together, setting the time-varying terms to 0, and just find out what happens, okay? Or what's the rate at which things happen. Okay, so let's see. All right, so what we're really interested in is what's the rate at which the various kinds of product are made, all right? And that's determined by, so to say, the so-called reaction velocity and how many of these bound complexes there are. So the first thing I have to do is to figure out what are the bound complexes, what is the value of the bound complex. And okay, so a little bit of fussing with equations gets us to something simple. Right, so if we put all of this together, we can say that the number or concentration of the, let S stand for the substrate, either E or B, A or B. It's the total concentration of the enzyme times K plus concentration of the substrate. This is going to be either A or B, and then K minus plus V plus K plus times S. Okay, for S is equal to A or B. So the idea is you take these equations, you set the left-hand side equals to 0, you eliminate E in favor of total, and you can discover that in equilibrium, the number of bound complexes for either A or B is going to have this dependence. Okay? All right, so what is that good for? Well, the rate at which product is being made, so ddt of product is equal to this reaction velocity times the total enzyme number or concentration times K plus S divided by K minus plus V max plus V, sorry, plus K plus S. Okay, so the idea is in steady state, there's some steady number or there's some constant number of bound enzymes bound to substrates, And that's producing product at a rate. And that's what we're interested in. This stuff is coming out, and we want to determine the rate at which it's coming out. So you wind up with something like this. All right. Where does this get us? Well, what we want to know is what's the rate of producing the good stuff as opposed to the bad stuff. So we basically want to take this for the, let's turn it around. We want to know what's the ratio of the bad product to the good product. So, you know, the bad product is B, let's say, and the good product is A. So I basically want the ratio of this for B to the same thing for A. All right, so the bottom line of all of this is going to be a fairly simple equation. And then we're going to have to stare at it and make some sensible decisions about what are reasonable values for the parameters. Okay, so let's see. All right, maybe we can put it here. All right, so okay. All right. So the error rate. So the ratio of the bad production rate to the good production rate is going to be just the bad times EB divided by good times EB and, sorry, times EA. All right, so this is the bound enzyme ready to make a product. This is the bound to the good guy. This is the enzyme bound to the bad guy, ready to make product. Okay, so we have a splendid final answer for the error rate, and it's going to be, I just want to make sure I put things together in the right order. All right, well, so it's going to be K plus prime times the concentration of the bad guy divided by K minus prime plus V prime. Then it's going to be the same thing upside down. K minus, this is for the good guy, divided by K plus for the good guy times the concentration. We're not entirely done. And then we have, this is all times V prime over V. All right, so you have to go through this algebra in detail, all right? But when we're all done, it's not so hard to see your way through it. Okay, what can we do? What can we do with this? So if you read the paper by Hopfield, and I suggest that you do that, he gives arguments for the following, sort of say, parameter simplifications. All right, so we're going to simplify the parameters. We're going to say, we're going to simplify the parameters. You know, in that picture we had of the transfer RNA, the stuff where you're binding, well, so to say, there's the side that's supposed to recognize the codon, and then there's the side that's carrying the amino acid. And they are very far apart from one another, all right? And this is presumably, if you think it through, it seems reasonable that the way the enzyme would work is that once something is bound, whether it's the good one or the bad one, it's hard to see how you could have much of a difference between the reaction rate. Okay, we're going to actually deposit the amino acid that's been dragged along permanently onto this transfer RNA. They give an argument, he gives an argument that says it's quite plausible that the actual reaction rate of the enzyme, once some possible, you know, once an amino acid has been bound to the enzyme, the actual rate of production of the charged transfer RNA shouldn't depend very much on whether it's the good guy or the bad guy. They're almost the same. Okay, so that's simplification number one. Simplification number two is, well, let's assume that the concentrations, the concentration of the substrates that we have to distinguish between is roughly the same. That makes sense because you have to have, in the case of DNA, you know that you have roughly equal amounts of A, C, T, and G nucleic acids floating about ready to be used because you never know. I mean, the usage rates are not exactly equal in the genome, but they're fairly close, all right? So you would expect to have roughly equal concentrations of the things that you're trying to sort. And the other thing is that for everything we've seen about how on rates go, tell you that the on rates have nothing much to do with the details of the thing that's going on. That just has to do with diffusion. And as long as the things that are going on are, have roughly the same diffusion constant, it makes sense to say that the on rates for the good guy and the bad guy are about the same. All right? So this is just to get your bearings. All right? So the bottom line, finally, is that the ratio under these simplifying assumptions. Okay, so now maybe we don't need this if you've already copied it. All right, so what have we got? All right, so bottom line. Is that, let's sort of say the zeroth order error rate, the rate at which we are making the wrong guy. Well, okay, various terms cancel out. There's not much left once I've made all of these simplifying assumptions. Okay, this is cool. We're getting somewhere. So this ratio is 1. The on rates, we said, are about the same, as are the concentrations. Therefore, these two guys cancel. So and also the reaction velocities are pretty much the same also. All right? So the bottom line is that this is the bad. Let's see, what do I want to say? Oh, I've got it the wrong way. The bottom line is that it's the off rate for the good guy plus the reaction velocity divided by the off rate for the bad guy plus the common reaction velocity. All right? So that's these two terms right here. All right? Makes sense. The off rate for the good guy should be small. The off rate for the bad guy should be large, right? I mean, this enzyme has to be doing something for us, and the thing that it clearly can do is once it's, it doesn't have much choice. Stuff is diffusing in on it. A good guy diffuses in, and it will hold on to it for a while and allow the next step, which is the creation of the product, to happen. A bad guy diffuses in. He doesn't have any control over that. It's there, but the enzyme had better be able to detect the difference between good and bad, and the right thing for it to do is as fast as it can to basically eject the bad guy and send it back into solution. So that means K minus and K minus prime had better be different. And K minus, the off rate for the good guy, should be small compared to the off rate for the bad guy. Now there's this V here. Okay, so what can we say about this? This is the basic result for a one-step discrimination, under reasonable conditions for these other variables, these other things that determine rates. And, okay, so this is some positive number. And clearly, if the reaction velocity is big compared to these off rates, so if V is large, this is just 1. All right? So what does V large mean? V large means the product is made before the enzyme gets a chance to discriminate. All right? If it's made so rapidly that the There's no opportunity for the bad guy to go off before the good guy gets fixed in place. So v goes to infinity is, so to say, the no discrimination is possible. So in order for discrimination to happen, this v can't be too big, all right? So in fact, what we know, so what does this mean? This means that depending on v, 1, that's v infinity, is bigger than f naught. And the smallest number you can get out of this is when v is 0, or anyway, small compared to either k minus or k minus prime, and that's going to be k minus over k minus prime. Okay, and this of course, you get this value only if, so you get the lower bound if v is slower than k minus and k minus prime, all right? You have to wait a long time. You have to wait a bit in order for the enzyme to make the discrimination, all right? Does that make sense? But in any case, the real point is that the best you can do, according to this, the most efficient, the most effective discrimination can be no better than the ratio of these two off rates. All right? Now, this makes sense, and what does this mean? So the best discrimination, best possible. All right? I mean, it could, who knows, right? The enzyme has its say in the matter. It controls what this production rate is. And if it's too big, I won't get to this best value. Well, we're trying to imagine a situation in which real discrimination can occur. So it had better, this will only be possible if this actual production rate, this reaction rate, is small enough. And small enough means it's got to be smaller than the off rate of either the bad guy, which is big, that should be easy because the off rate for the bad guy is big, or the off rate for the good guy. The reaction rate has got to be less than the reaction rate for the good guy. The off rate for the good guy, which is supposed to be small. All right, so the best possible is this ratio, and of course we have just shown earlier on that in general these off rates are governed by the binding energy, right? So so basically this is going to be, when we're all is said and done, this is going to be e to the minus beta times the energy difference. Let's call it delta. It's really the so-called free energy difference, but I'm not going to try to make it. So this is, let's see if we can get it right. E bad minus E good. Okay, so presumably the binding is less strong for B than it is for A. So this is a positive number, all right? And okay, multiply that by beta or divide it by KT and put it up in the exponential with a minus sign. This is a small number, all right? How small can it be? So the idea is the other stuff in the off rate, the 1 over tau off, the stuff that can be different between the two guys is this number, is the binding energy. All right? So basically this, and the best possible discrimination, therefore, when we're all done, this best possible discrimination is the exponential of the difference in the binding energies divided by KT. So fine. Is this bad or is this good? All right, so this is a long song and dance to get to an answer that you probably would have regarded as quasi-obvious, although you really have to, it's apparently not obvious because we had to make some choices about parameters, and the really important one is that we had to choose that the reaction rate was slow, right? That is to say, the rate at which this is happening is slow. And in that case, and slow means something very specific, And in that case, we get this number. Okay, so is this good enough? Well, what are we talking about? The various examples of this are, what we're missing is a hydrogen bond or two, something like that. That's the typical difference between the things that are confusable, let's put it that way, by the enzyme, is small fractions of an EV. And if you put in reasonable numbers for the 300K at which we live, this number is typically on the order of 10 to the minus 4. It's e to the minus 10 or 10 to the minus 4. Okay? Now, people knew this well before 1974, right? But people didn't, they either said, oh, okay, all right, somehow it must work out. But this is clearly a problem. If you're copying DNA and you make a mistake 1 in 10 to the 4 times, this is an enormous mutation rate. You simply can't live with that. It's also not good when you're making proteins from messenger RNA. 10 to the minus 4, well, that kind of means you're making a mistake every time you make a real protein. This is not good, okay? So, but the place where it's really, really, really just overwhelming you is in the copying of DNA. There measurements can be made, and you can discover that the actual error rate is like 1 in 10 to the 8 or something like that. How the heck can you do that? That's the question. How is it possible to get the observed error rate for copying DNA, which is 10 to the minus, 1 in 10 to the 8, roughly speaking? Although we know that in many examples. It's maybe for proteins, okay, badly copied, badly created proteins that do not faithfully decode the message. Well, that's problematic. Sometimes it's really important that the protein, we know that single point mutations in proteins can cause substantial problems. It can make them misfold. All kinds of diseases are in fact due to single point mutations in proteins. That is to say, the wrong amino acid in one place. Okay, so, but you could imagine life living with this kind of error rate for proteins, but it would be pretty troubling, and presumably you'd like to do better. And you know that you have to do better for copying DNA, that's for sure, all right? The sanctity of the genetic code, the importance of keeping it pure, not letting it wander so stochastically is obvious. Yes? So we're not done, okay? We're going to solve the problem.
I guess the one thing that is not entirely clear to me is, so these enzymes that we're looking at, they have some degree of specificity, right? Because
yes,
if it's the same enzyme that has to attach, let's say, to different kinds of amino acids or whatever, I mean, eventually even if it's the wrong one for right now, eventually you might need that wrong amino acid some steps down the polymer chain, right? So I guess what we're looking at is a situation where the enzyme has to have this kind of specificity. This is the problem
yes,
that I'm not understanding.
Yes, absolutely. So let's take, I mean, the simplest context, at least. The biochemistry can be complicated, and I don't have my arms fully around all of it. I'm a physicist, not a chemist, and chemistry is hard. There's just no question about it. Okay, but think about charging the transfer RNA. All right, it's kind of it's a one-off. You have this transfer RNA whose job is to take the codon, whatever, U something something, and turn it into phenylalanine, whatever. Just each amino acid has its code, and each such amino acid code pair is implemented by having a particular transfer RNA and a particular enzyme. Okay, you have to have just the right, you have to have an enzyme whose job it is to take the uncharged transfer RNA, right, the guy that has just RNA and no amino acid attached to it, and attach to it the right enzyme. So you have to have a specific enzyme. So for each codon, there's a specific enzyme, a protein whose job it is to take the uncharged transfer RNA and put the right amino acid on it. Okay, so it knows, it is designed to discriminate. Okay, now I'm not sure if I'm answering your question.
Yeah. So.
But anyway, it's not a question of down the line. If he makes a transfer RNA that has the wrong amino acid attached to it, that means that when that charged transfer RNA is called to action, it's going to transfer the wrong amino acid to the growing protein. Okay? So, the idea is you'd better have a pretty high accuracy of picking out the right amino acid to charge, to actually attach to its correct transfer RNA. All right? You don't want too many, you're making actually what you're doing is you're making a pool of charged transfer RNA. And the question is, what fraction of that pool has the correct association between a triplet RNA base and an amino acid, okay? So the other context is you have a growing chain polymer, and you're trying to make sure that you have the right thing. Each step, there's a correct entity to add. And if you add, and we're calculating the generic value of what's the probability that I will add the wrong thing to this growing DNA, well, this growing polymer, all right? So in the cell, there's just one DNA. There are lots and lots of RNAs and lots of proteins. So the problem is maybe less dramatic for transcribing RNA and translating RNA, but it's very dramatic for copying DNA, okay? All right, so anyway.
Yeah, so just because this makes it much clearer. So the context is that these enzymes that would eventually have a preference for, say, B, they are not floating around at the moment, right? Right now we have just produced the enzymes for A.
Well, this is the enzyme. Okay, okay. Let's put an A on the enzyme. This is the enzyme whose job it is to pick A out of the soup and do something with it. All right. And I'm saying that it's that enzyme can also pick B out of the soup, but it does so less often because it is able to discriminate. It discriminates on the basis of in the end, on the basis of some energy difference. All right? When it gets the wrong guy, right, it doesn't have any choice. The stuff is, the A's and the B's are diffusing. When a B happens to hit it and stick, then it'll get bounced off more rapidly than when an A hits it and sticks. Okay? So this enzyme is a protein that is specifically constructed to keep A's and do something with them and reject everybody else. So here I'm just imagining there's only two options. It's an A or a B. Okay? Mm. You can do experiments in which that's exactly what's available. You do in vitro experiments in which you have the enzyme that's supposed to pick alanine. I don't know. I mean, I don't have in my head. There are pairs of amino acids that are very similar in structure. So take any such very similar pair. There's an enzyme that's supposed to pick one of them out and not the other, and it has to be able to discriminate in the sense of when the other hits it, it bounces. It's not that it bounces off, but it is released rapidly. Whereas when the right one hits it, it is not released rapidly. It stays along for a while. Okay. All right. So this is good, right? Right. And these rates are never zero. All right. So anyway, this is telling us if you just have usual sort of say one-step kinetics, this is the best you can do. right? One readily understands what's the order of magnitude of these energy differences. They're, of order a couple of hydrogen bonds or something like that, 10 kT, let's say, okay? And that turns out, so that's such a number at 300 degrees K, and, we have to live at 300 degrees K, and we have to have an accuracy in reproducing the DNA, which is basically the square of this. I mean, that's what we observe. Well, that's sort of suggestive. If it's the square, it's as if it suggests that you ought to imagine, maybe we should imagine a two-step process in which this kind of discrimination is allowed to happen twice, okay? So that's exactly, so this is the Hopfield and Nino idea, that in order to beat this energetically determined, so to say, lower limit on the discrimination of these enzymes, maybe we discriminate twice. So can we do that? All right, so we will now invent another scheme in which basically you get to try twice. Now, as we will see if I actually get there, there's no free lunch. So there will be, it will be possible basically to get a discrimination which is this times itself. You do it twice. But this is going to cause the process to be very energy inefficient and very slow. But maybe it doesn't matter. Maybe accuracy is more important than speed, okay? Anyway, that's the general idea. So, new scheme, the Hopfield-Nino scheme. And the basic idea is just to do what we did once, twice. All right, so what does it look like? So I have an enzyme, and I have a substrate. So the substrate is the good guy or the bad guy, the A or the B, Mr. Wrong or Mr. Right. And I'm trying to discriminate them. And so this is an enzyme. It's in the soup of these guys. And every now and then, one of them will stick to the enzyme. So lands in a pocket or something like that. And so there's some rate for this to happen. And this rate, okay, so this is the same story as before. The bigger the concentration, the faster the rate. This is determined basically by diffusion. It's nothing special. It can go backwards. So there's a K minus. All right, now the idea is that this complex of the enzyme and the substrate can, at the cost of some energy, do something. In other words, the enzyme can, it's got a substrate attached to it, and now it changes conformation. You make a bond or something like that. So in this new, and the idea is, things are arranged so that this is irreversible, or as close to irreversible as you can. And that's why it must consume energy. If it was in thermal equilibrium, that would be fine. It wouldn't consume any energy, but it would go back and forth, and we will see that that would essentially defeat the purpose here. So this is treated as an irreversible process, which means that the rate at which it goes forward is much, much greater than the rate that it goes backward, much, much greater than it would be in equilibrium of all of the reactions we're going to put together. And so we're just going to forget about the backward rate. We're going to assume that somehow we are coupling this process to energy source somewhere else, the ATP store inside the cell. So this is treated as an irreversible step. Okay, and at this point, this guy can either make the product at some rate, the charged transfer RNA or the new base in the growing double-stranded DNA or the new amino acid in the growing protein chain, or, and that's the key, it can unbind at some rate, which we'll call L minus. Okay, and that's the key. In other words, this guy, so eventually we'll write down the equations for this is the right substrate or the wrong substrate. It's two different guys. There are two different rates involved. The on rates are about the same, but the off rates are different. So, you'll have more complexes here where the right thing is bound as opposed to the wrong thing. But that discrimination will be, so to say, at this level. And if things happen at the right, fast enough, if this guy happens very fast, there's now a new setup, a new situation in which essentially to a new enzyme, a new conformation of the enzyme, the good guy or the bad guy are bound, and we have an opportunity for a differentiation between the off rate of the good guy as opposed to the off rate of the bad guy, okay? And putting these two things together is not too surprising that we'll essentially generate a discrimination which goes as the square of the one-step discrimination, all right? So this is an abstract scheme. Is this possible? Or if you can achieve this, then what happens? All right, so you have to write down the set of kinetic equations. You have to go through the algebra of deciding, what happens if I'm in steady state. It's not quite equilibrium because this is irreversible. I just go one way here, in concept at any rate. But anyway, go through the same line of argument as we did before. All right, and so we're going to find something like this. We're going to find that the reaction, and again, we'll make the same kind of parameter assumptions that we made before. It doesn't matter, the reaction velocity is the same whether it's the good complex or whether the good substrate is bound or the bad substrate is bound. The concentrations are the same, the on rates are the same. So we'll assume all of those things. We could also have let's see, do we have it here? L minus. I've ignored the possibility of this guy going forward. We could put that back in, but for the moment, let's not. This is some high energy state, and it's very unlikely that somebody will actually stick, let's say. Let's assume that's the case. All right, so now, the bad product rate is going to be V times the bad complex excited, right? The outcome of that fellow times E good star. So there'll be some factors. There's going to be, all right, so I write it out. L minus plus V divided by L minus prime. Let's in fact just give them names, A and B. So there's a second factor, K minus A plus M plus divided by K minus B plus M plus. So, there's some discrimination that happens here where I'm competing between the unbinding and the making of the product. And there's some discrimination that happens here where I'm competing between the unbinding and the, so to say, next step where I'm not actually creating the product, but I'm creating this second state of the enzyme. Okay? So this is slightly more complicated, but you see that there are two factors. This is the kind of factor we had the first time for the one-step process, and then there's a parallel sort of factor which is describing what's happening at this intermediate irreversible step. Okay, now, if I can, so there are two rates that have to be controlled. So for the one-step process, I had to have the reaction rate slow compared to the unbinding rates, the smallest unbinding rate, in order to get the minimum possible error rate. So I have to, in order to get this factor to be as small as possible, I have to make V small, the reaction velocity compared to K to L minus and A and L minus B. So I want to make this factor as small as possible. I make the reaction rate small. I want to make this guy small, and that means I've got to make the conversion rate, this irreversible guy, small. All right, so I have to make M plus small compared to K minus A and K minus B. I mean, one of them, in both cases, the good off rate is small already. It's got to be smaller than the bad off rate. Discrimination means you kick off the bad guy quickly. So there are two such requirements. So that means the rate at which stuff is making its way through this chain to the output is, so to say, doubly small, right? However, if I'm willing to do that, if I'm willing to accept that, then of course what do I get? I get L minus A over L minus B times K minus A over K minus B. And the argument that each of these ratios, these off rates, have a ratio which is governed by a binding energy difference divided by KT, that argument is just as valid. There are two different enzymatic steps. I'm discriminating on the basis of binding energy in two different situations, and the general rule that the ratio of off rates is determined primarily by the exponential of the difference of the binding energies of the two substrates divided by KT, that holds. And so you expect this to be roughly the square of e to the minus beta epsilon bad minus epsilon good squared. All right? So that was the goal. It was basically to do this first step, which is getting something done, but not enough, to somehow do it twice. And clearly, the way to do it is something that can't happen, will not happen in equilibrium. You have to imagine an essentially irreversible step in the process. That means energy has to be consumed. All right? And if you look at the way the parameters are involved, the whole process has to be slow. Right? Okay, so if you're copying DNA, that's not really a problem, because the event in which a cell copies itself to make a daughter cell, well, usually there's a fair amount of time to do that. You don't have to do that in a millisecond. You can take, in fact, our cells take hours to do it, right? So that's really not a problem. And if you're also, the energy issue is not really a problem, because the genome is really valuable, and you're perfectly you're authorized to spend a lot of energy copying it, because you only do it once in the lifetime of a so to say per division lifetime. So the actual rate of consumption of energy is not so bad. Making protein is another matter. I mean, there are times when you have to, for example, in embryonic development, especially in lower organisms, the various stages in making an embryo grow from a single fertilized egg to 10 to the something cells, that has to happen in a relatively compressed time scale. And that means you've got to build a lot of proteins. You have to really churn them out at a high rate. And therefore, this kind of correction problem, or this correction scheme, if the slowing down is big enough, could be a problem. Now, these are all things that people debate with great heat, and it's not all sorted out, right? So there are many, many questions that are left. But the basic scheme is something that I think by now everybody agrees. It must be essentially this. There's really no other way to go. Now, where do we want to go from this? Okay, so I will perhaps, there's a very nice bit of software that Phil Nelson has created with some colleagues, which essentially turns this reaction scheme into a simulation. And you do a Gillespie algorithm simulation of what happens as a function of time. And it's rather cool because when you're all done, you can see how many, you have one enzyme and it's cycling through a bunch of states. It's either here, bound to the good guy, or bound to the bad guy. Or it's here, bound to the good guy or the bad guy. Or it's kicked something out, it's made a product. And so you can follow what happens as a function of time. And you can count, so the idea, every time you're giving yourself another option to discriminate by essentially backing off this, at this point in the pathway, you're basically wasting the energy that you used to go from this bound complex to this excited bound complex. So you throw away at least an ATP every time you do this. So it's kind of interesting to look at how often you do this, so to say, wasteful step in making a highly accurate copy. And so we can do analytic analyses of that, but they get kind of opaque, and it's very, I would say, instructive to see a simulation of this kind of scheme, and just look at what happens typically. How many ATPs do you waste in order to not, how shall I put it? If you look at how many ATPs it takes to create a perfect copy of whatever you're trying to copy, or a copy that has, you know, one mistake per 100 or one mistake per 1,000. You can play all kinds of games. So I think I will. I mean, I've posted some of the I've posted the essential software on our Google Drive, and I'll perhaps walk you through it a little bit tomorrow, to so that you can appreciate. I think this is very very abstract stuff, but it's very helpful to see what the actual stochastic variability of things looks like in order to have things that happen, so to say, in a time span that can hold your interest. You have to choose parameters for values that are actually reasonably far away from realistic values, but still you can learn a lot by playing games with the parameters. Okay, so we'll pick up this tomorrow. But anyway, that's the introduction to the basic idea of what's called kinetic proofreading. The basic idea, that is, how do you discriminate the right from the wrong when the energy difference between the right and the wrong is too small to give you a thermodynamic discrimination between them that's big enough to get the level of accuracy that you need. You need things like this in copying DNA. You need things like this in, so to say, translating message into protein. It turns out you need the same thing in the functioning of the immune system. Immune cells detect bad guys because, well, immune cells are constructed to detect particular pathogens, and they've got to distinguish between, well, I'll talk about the immune system eventually, but anyway, the fundamental qualitative problem of discriminating good from bad when the energy difference between good and bad is not that big arises there also. So it's a very generic problem in understanding how living cells function, and I think it's a good thing to know how it works. So, you know, I would recommend going through the algebra here so that you can believe it. But, you know, when we're all done, the general idea looks pretty clear. You're doing what you were able to, I think, see pretty clearly in the one-step process. You're just doing it twice. And so the discrimination phenomenon gets multiplied, gets raised to the second power. You don't seem to need to go any further, although I gather people have found instances where, so to say, multi-step discrimination is helpful. And there continues to be, since this is an abstract scheme, not based on really specific, it's an abstract scheme, and we don't have, I'm not telling you about specific enzymes that are doing this, although we can map it onto specific enzymes. I could also, probably should tell you about the experiments that Hopfield managed to get done. He's a theorist, so doesn't do experiments. He convinces experimentalists to invest their time and energy in doing the experiments. But the experiment that was done a couple of years after his proposal to show that something like this must be happening is, I think, quite interesting to describe. So we'll talk about that next time. Okay? Thank you.